Okay, so we're on to our final type of motion, right? Simple harmonic motion. Okay, so we've had linear motion, straight line, circular motion, okay, and now we've got simple harmonic motion. And simple harmonic motion basically is when something is oscillating, okay, oscillating up and down, all right, okay. Could be a pendulum, could be a spring, could be a ruler vibrating at the end of a wall, it could be your eardrum vibrating. In fact, simple harmonic motion, or items moving at close to simple harmonic motion, is the most common motion in reality that we experience. Okay, so let's have a look. 3 steps. We always draw. This is our spring before we start. Okay, and then we add a weight. Okay, so we're adding a weight. So we're going to add a 1 Newton weight to it. Okay, and clearly there's an extension. Okay, a displacement, and that displacement, I'm going to draw that in. Okay, I'm going to call that displacement SH because it's related to Hooke's law, and I'm going to put in the weight. Okay, right, so that's the displacement. Now, what's important here is that displacement, in this situation for Hooke's law, everything is at rest. Okay, so it doesn't look like it's at rest, but we're dealing in a situation where it's at rest. Okay, right, now let's draw a free body diagram. Okay, a free body diagram of it. Okay, at this stage there's a weight down, there's a mass, it's on the earth, there's a weight down, you have your first arrow drawn, and it's at rest, the body is at rest, so therefore the other weight, the weight up, a force up called the restoring force, and that must be equal to the weight down. That's the restoring force. Okay, and there's a relationship between the restoring force and the displacement. There's a relationship between the restoring force and the displacement. Okay, if I increase the weight, okay, I've increased the weight is equal to the restoring force, so I've clearly increased the restoring force, I doubled it, and you would find that this displacement has also doubled. So the restoring force is directly proportional to the displacement. So restoring force is directly proportional to displacement, so restoring force is equal to a constant times the displacement, and the constant is called the spring constant. Okay, and basically the spring constant, if you think about it, it's F divided by S. It's the newtons per meter. It's how many newtons you would have to apply to get the displacement to be 1 meter. Okay, and it tells you how strong the spring is, how stretchy it is. Okay, right, that's the spring constant. Now, where does the minus come from? The minus is because the displacement is down and the restoring force is up, so they're in opposite directions, so therefore that's why we have a minus. You wouldn't have to worry too much about that. Second issue, okay, I'm going to take away this one now so you can see it quite well. Okay, if I now decide at this stage to apply another, to move this down to make the displacement greater, this is a new displacement, this is the crucial point, this is a new displacement, and I'm going to call it SS for simple harmonic. Okay, so watch, we draw a diagram again, and this time we've brought the weight down to here. Okay, so there's been an increase, that's the increase. Okay, SS, you could also look at it here, it's the same, but I'm looking at it here, and basically what's going to happen is that weight is going to oscillate up and down around that point, so that's the rest point. Okay, that's the rest point. So let's have a look. So that's the rest point there. Okay, that's not very well drawn, but that's the rest point. Okay, and I'm going to oscillate it up and down, so you can see it's oscillating there beautifully. Okay, right, now the acceleration is proportional to the displacement, and if simple harmonic motion takes place, the acceleration is always proportional to the displacement. In other words, the greater the displacement from the rest position, the greater the acceleration. So the acceleration is maximum at the extremities, and it's actually 0 as it passes the middle position, because S is 0. Okay, because it's proportional to, it is equal to a constant, and a constant we call omega. Okay, why do we call it omega? It's linked, there's a link between it and circular motion. It's not angular velocity, there is a link, and there's a very good clip later which will be compulsory, you will watch it, okay, which kind of gives you that, explains that to you in a very, very nice way. So something to look forward to. Right, okay, now you may ask yourself, where does this omega squared come from, and where am I going to get it? So we've more work to do before we start doing our calculations tomorrow. So there are 2 formulae. Okay, there are two formulae, right? We now want to look at how we can go from this to this, and it gives us another formula that is useful to us as we go. Okay, so just 1 second there now. Okay, so you may be asked to show that A is proportional to S using Hooke's law or something like that. So it's a derivation. So we start with F is equal to minus Ks, right? Hooke's law. We also write our simple form of Newton's law. Okay, F is equal to ma is a special case. So we write that down. F is equal to ma, right? Both forces are the same. Okay, so we say ma is equal to minus Ks. We rearrange. A is equal to minus K over m times S. And we write underneath that then A is equal to minus omega times S, and we're done. Okay, where omega squared is K over M. Now that's crucial. Okay, you need to know that. Okay, you might, if you want to drive it every time you can, or if I was you, I'd learn it. So omega squared is equal to K over M. Okay, omega squared is equal to K over M. And on top of that, okay, on top of that, right, we can then get periodic time. Okay, because notice, look, that oscillates up and down, it has a periodic time. Okay, time for one oscillation. Okay, now the periodic time formula is the same as the formula for circular motion, and that'll make sense to you when you look at the at the clip later. But what I'm saying to you, and it's where it shows up in the maths tables actually, is T is 2 pi over omega. It's the periodic time for circular motion where omega is angular velocity, and it is the correct is formula for circular or for periodic time for simple harmonic motion where omega is a constant, but omega squared is equal to K over M. Okay, right, omega squared is equal to K over M. So from that you're in business. Okay, now I'm going to be adding the clip for calculations tomorrow, okay, as part of this lesson, so you'll be doing it tomorrow. Okay, but that's that's it. They are the 1 second, 1, 2, move that down twice, 3, 4. That's the toolkit. That's what you'll be using in all simple harmonic motion questions. The problem people have is they get the S's mixed up. They think these S's are the same. Very rarely they are. Usually they're different S's. Okay, all right, talk again tomorrow. Bye bye.